Welcome back. We're continuing solving rational equations and inequalities, solving inequalities, which is just another way of making true statements. In this example, we're going to solve the inequality x over x plus 2 plus 1 over x minus 1 is less than or equal to 3 halves. In our last problem, we had a less than instead of a less than or equal to, and everything in our last problem, we ended up with open circles at all of the points, and so it wasn't really clear why we had open circles some places and what would make a closed circle. In this problem, we're going to see a nice mixture of open circle and closed circle. So, our steps to solving these, we are going to start by stating our excluded values. And the excluded values, that's just another way of saying our domain restrictions, which is just another way of saying that we can't divide by 0. So when I find my domain restrictions for this problem, my first denominator gives me x cannot be equal to -2, and my second denominator gives me x cannot be equal to 1. So I got my domain restrictions from there. My problem is fully factored, so now I'm just looking for my least common denominator because I'm going to solve the related equation, which requires me to find the least common denominator. So my least common denominator for this problem, my first term has an x plus 2, my second has an x minus 1, and my third has 2. So it's x plus 2 times x minus 1 times 2. Solving my related equation. So the equation is x over x plus 2 plus 1 over x minus 1 is equal to 3 halves. Just replacing that inequality symbol with an equation. Okay, I'm going to multiply both sides by that least common denominator. So that's x plus 2 times x minus 1 times 2, x plus 2 times x minus 1 times 2. All right, when I take this and multiply it by the first term here, my x plus 2's will cancel. So I will get x times x minus 1 times 2. When I take it and multiply it here, the x minus 1's will cancel. So I will just have plus 1 times x plus 2 times 2. And over here, the 2's will cancel, so this will be 3 times x plus 2 times x minus 1. All right, I am going to multiply this out. So this will give me 2x squared minus 2x plus 2x plus 4 when I multiply all of these out. And then over here is equal to 3 times x squared plus x minus 2. Combining things, 2x squared plus 4 is equal to 3x squared plus x minus 2. Nope, plus 3x minus 6. You want to make sure you distribute that in. It's really easy to make mistakes like that. So this is minus 6 plus 3x. I'm going to bring everything over to the right-hand side, and I get x squared plus 3x minus 10. This is factorable, so this will give me x plus 5 times x minus 2. So x is equal to -5 or +2. So my critical values are going to be x is equal to -5 and 2, and x is not equal to -2 and 1. Now, the situation, the domain restrictions are an x is not equal to. The not equal to symbol is always going to mean that I'm going to have an open circle. The values that come from my solving, that inequality symbol is going to go with the inequality symbol from my original problem. One way of thinking about this is I'm trying to make a true statement. If I plug -5 in here, I expect to get a true statement. So let's just check that out. So I have -5 divided by -5 plus 2 plus 1 divided by negative 5 minus 1. All right, 1.5. That is equal to 3/2, so it is a solution. And if I do the same thing with 2, I'll also get a true statement because it's less than or equal to, and these give me the equal to situation. So because I have a less than or equal to in my problem, these are going to be graphed with a shaded in circle. So our solutions go along with the original inequality symbol. Our domain restrictions always get an open circle. Okay, so I've got -5, -2, 1, and 2. -5 and 2 are going to get shaded circles. -2 and 1 are going to get open circles. These come from my solutions. These come from domain restrictions. Now, I need to pick points in each of these different regions and test them on my calculator. So I'm going to go with maybe -6, -3, 0, 1.5, and 3. I'm going to go about this just like I did before. If you needed to check these by hand or without a calculator, you could. It's just going to take you a lot more time. So in y1, I'm going to put the left-hand side of this equation. So that is x divided by x plus 2 plus 1 divided by x minus 1. And in y2, I'm going to put 3/2. I don't really even need to put 3/2 because I know that I am checking if some value is less than or equal to 1.5. So for each of these, I am plugging in these values of x and seeing if the value of y is less than or equal to 1.5. My table is set for independent ask, and I did that by hitting the second button and then the window button to pull up my table setup. I set that to ask, and then I go over to my table. For an x value of -6, I have 1.36 is less than or equal to 1.5. And that is a true statement, so I'll put a happy face. If I plug in -3, so I'm plugging in these circled values, I get 2.75 is less than or equal to 1.5. That is not a true statement, so I'm seeing if this number is less than or equal to that number. Not a true statement, so that is a sad face. If I plug in 0, I get -1 is less than or equal to 1.5. That is a true statement. If I plug in 1.5, I get 2.4 is less than or equal to 1.5. That is not true. And if I plug in 3, I get 1.1 is less than or equal to 1.5, which is true. All of the regions with happy faces get shaded in, and they are part of my solution set. And then I'm just going to write these regions in interval notation as my solution. So this is going to be -infinity to -5 included, union, -2 not included to 1 not included, union, 2 included to positive infinity. Any value in one of these regions will give me a true statement. So if I plug in -1,000, I should get a statement that's true. If I plug in 1,000, I also get a statement that's true. If I plug in -1.9, I also get a statement that's true. If I plug in 0.9, I get a statement that's true. So any value in these three regions is going to give me a true statement.